Okay, so let's imagine that you were asked what is the reaction product when you mix together formic acid and NaOH. And this is something that you could have done in, say, Chem 110, where you have HCOOH plus NaOH leads to new things. And if you recognize that this is an acid and this is a base, then when you react an acid and a base together, you make water and a salt. And so this is something that you may be familiar with from your previous chemistry work. But now let's go ahead and actually think about the reaction involved. And with the land of organic chemistry, what a reaction will always be is a series of curved arrows. And so what I have here is an oxygen that has a lot of electron density, and so it's going to make a new bond to this hydrogen. And when that happens, it's going to break the bond that was already there between the oxygen and the hydrogen and push those electrons onto that oxygen, which will then create two new products. And so what I've shown in the red arrows is the movement of electrons. So this lone pair is making a bond to that H, which generates water, and then this lone pair, which was between the oxygen and the H, now becomes a lone pair. This bond between the oxygen and the H now shifts to become a lone pair that belongs to the oxygen because the hydrogen has now gone away. So the result of drawing this arrow is now you've got a bond between the H and the OH that you had before. In other words, this is how you generate the water, and this is the Lewis structure that is boring and not particularly interesting, whereas the lone pair that results on the other side now creates an interesting resonance thing to think about. So in other words, I would go ahead and draw the initial product of this reaction as follows. An oxygen with a minus on it, an oxygen with a double bond, and so on. And if you look at these two oxygens, you will get the distinct impression that the two oxygens are different. One has more minus on it than the other, one is more neutral, one has a double bond, so it should be a shorter bond, one has a single bond, so it should be a longer bond, and so on. But this is a poor understanding of what this molecule actually looks like. So instead, let's consider the resonance format here. This molecule is drawn, again, all I'm doing is redrawing it, is showing a minus localized on that oxygen. But now we should think about which kind of resonance images would exist for this molecule. And the main reason why I started with this sort of curved arrow formalism is if you want to move around with resonance, you're going to need to be using those curved arrows. And the way the curved arrows always work is they start where there's a lot of electron density and they go to where the electron density is going to end up. So if you're looking at this molecule and you see a problem, the problem is this oxygen has too much electron density. It is minus right now and does not want to be. And so the way you solve that is you push the electron density to create a double bond. You are now going to share some of that electron density with this carbon. But how many bonds does this carbon currently have? Well, it has 4, and it cannot tolerate any more. So if you are making a double bond there, then you're going to have to force a double bond to leave, or a bond to leave. And this carbon has a hydrogen that can't leave in any meaningful sense, and it has a double bond here. But you could take this double bond and push its electrons to become an oxygen lone pair. That would be okay. So the end result of the two arrows that I drew is going to be that the oxygen up top is now the one that has a minus on it, and the oxygen that's on the lower right is now the neutral one. And this is another resonance structure that would be correct, plausibly, for the structure that depicts this molecule. Now, of course, if you would like to move back in the other direction, all you have to do is take this lone pair and create a double bond with it, and that will create too many bonds on that carbon. So as to solve that problem, you then take one of the double bond lone pair pairs of electrons, bonding pairs of electrons, and push it to be a lone pair on that oxygen, and that moves you back in this direction. And again, much like with the benzene situation, the reality of this molecule isn't either structure. The reality of the molecule is instead a weighted average, a superposition of the two structures. So in other words, I would prefer not to draw either oxygen as having a double bond. I would prefer to draw a little bit of double bond character between each one and the carbon, and I would also like to draw a little bit of single bond character. So it's basically not a double bond and a single bond. It is instead a 1.5 bond on either side. I don't want to think of this oxygen as having a minus and this oxygen as being neutral. I will instead want to think of each oxygen as having minus 1/2 on it. I don't want to think of each oxygen as having either 2 lone pairs or 3 lone pairs. I want it to have kind of the density that's in between, 2.5 lone pairs, if you will. So in other words, the way the structure should actually look, if we measure, is not either either individual resonance structure, neither of which is actually real, but instead the weighted average of both resonance structures. Instead, it should look like this. So far, I've shown you two examples of why we would do resonance structures, and in both cases, what we're trying to do is show what the actual structure looks like. Again, the impression given by these individual resonance structures is shorter bond, longer bond, and the reality in both cases was, in fact, that there's going to be symmetry here, that this molecule will be symmetrical if you look at it from the outside, that there's an even amount of charge on both oxygens, there's an even bond strength on both oxygens, and that the bond lengths are the same in both cases. So fundamentally, one of the reasons to do resonance structures, to do a combination of Lewis structures, to mentally average it, is because the structure is going to be different than what you imagine when you look at any single resonance structure. And instead, what you always need to be thinking about is the weighted average of them. And when I keep saying the term weighted average, what I mean is these two have the same energy, so they should contribute 50-50 to the final structure. That won't always be the case. You will encounter situations where one resonance structure is much more important than the other ones. It has a lower energy. It describes the molecule better in some ways. But if you have two even structures, then the weighted average is going to be essentially 50-50. And if you have several different structures where one is really good and the others are kind of bad, then it's going to look mostly like the really good one. That's the weighting. The weighting is by the energy. The lower energy of the resonance structure, the more important that is, the more it contributes to the final weighted average.
So once again, I'm going to show you a quick bit of work in Gaussian to show the result of the formate ion that is formed. And you have, as the initial thing before optimization, a CO single bond that has a minus on it, and this bond is 1.43 angstroms on average for a CO single bond. And a CO double bond, again, on average would be 1.26 angstroms. So this is what it looks like before you optimize. And again, this is sort of a resonance contributor picture where there is a single Lewis structure. But once you optimize and you allow it to find the lowest possible energy, the result that you get looks instead like this. And you can see the clear symmetry here. And in fact, the bond length ends up being 1.23 angstroms on both sides. And so what's odd here is that it actually ends up being shorter. Now, the reason why that happens is because these are generic bond lengths, and then once you optimize, it realizes that it has a minus charge and optimizes the geometry to end up in a better place. And so it achieves that largely by having tighter bonds than you think. There's more electron density in this molecule than it thought when you were constructing it. But the big picture idea is, once again, that would be the way you would draw it in Lewis structure form, but then when you optimize it, the way the molecule actually looks is symmetrical. So once again, our Lewis image is not capable of giving us this unless we invoke resonance, and unless we draw several different Lewis structures and average them together and realize that the actual molecule looks like this. And once again, this is calculated, but enough physical chemistry has been performed on similar molecules that we actually know that formate truly is symmetrical, and we know the bond angles and bond lengths and so on and so forth. So this data has in fact been checked against experiments. Once again, if you draw a single Lewis structure, but there's charge, double bonds, if a pi system is involved, then you need to at least contemplate the other resonance structures so you have a fuller picture as to what the molecule really looks like and how it acts.